Okay, hello. This is my presentation on logic and Venn diagrams, and on the right I have a little funny thing. Let me know if you get it. Okay, so let's first have a look at the outputs of each of the gates, which I'm sure have probably been gone over before, but let's go over it again. It's never harmful to practice. So an AND gate outputs a 1 if both of the inputs are 1, whereas an OR gate outputs a 1 if any of the inputs are 1 or both. So if they're both off, it produces 0, but if any or both of the outputs are on, it produces an on. A NOT gate is also an inverter, so a 0 becomes a 1 and a 1 becomes a 0. This is the only logic gate that has only one input. Now we come on to the more complicated ones. So the NAND gate, this is pretty much a NOT AND gate. So it's a combination of the AND gate and the NOT gate. So it outputs an inverted signal of what an AND gate does. So if both are ones, then it produces 0, whereas any other input or combination of ones and zeros is on. So think of this as the inversion of this. So 0 becomes 1, 1 becomes a 0. Then a NOT OR gate is the same kind of thing as a NAND. It's a NOT OR gate. Sorry, I think I said not OR, it's a NOR gate. So here we have, it's the inversion of these outputs here. So 0, 0 is a 1, and anything with a 1 becomes a 0. And then the XOR gate, which is pretty much, it's called an exclusive OR gate. So if we have a 0, 0, it has a 0, and if we have a 1, 1, it has a 0. So it's only if one of the inputs are on that it produces a 1. Okay, let's move on. So the IB has its own representations for the 6 gates. There are the standard ones that everyone recognizes, but the IB's ones are much easier. It's just a circle with the required number of lines going in and the word in the middle, and then the required output, which is always 1. So if you can also be writing logic statements, which are statements of a logic diagram. So when you're writing logic statements, you use these symbols here, which correspond to different logic gates. So for instance, the ampersand is for AND. So let's say you want to say you've got two inputs, P and Q. Then if you wanted to have an input of, if you wanted to do an AND of P and Q, then you do P ampersand Q, and then that would represent P and Q. Okay, let's come on to our first example. So this is our logic statement here. P and not Q or not S. Okay, so let's break this out. So we have a bracket here with P and not Q. So this not Q is 1 unit. So first we have to invert the Q input. So that's what this not gate here does. And then we take the two outputs of those and put it into an AND gate. So this will only go on if both of these inputs are 1. Then it ORs with the inversion of S. So we need to then get the inversion of S. So that's what this S and the NOT gate does. Then both of those go into the input of the OR gate, and then that produces the output over here. Now let's go on to a slightly harder one. Now this one looks a lot more complicated. Oh wait, sorry, I didn't explain this. So here's an example of the logic statement. So P and Q, and then the exclamation point is to say not Q. And then the double straight lines, which will be similar to the way we use it in Java, is OR. Okay, so now moving on to this diagram, we have P and Q, or P XOR P and R and Q. Okay, so this is quite a complicated one. So let's just break it down. So we have this statement here, and this big statement here, which is connected with an OR. And then within this statement, we've got this statement, which is connected to this statement here. So you just kind of have to break it down into the smaller pieces to understand what you're looking at. So let's start with this one over here. So the P and the Q go into the AND. So just ignore these dots because these are just leading into the other bits because you only have 3 inputs. So P and Q, you get the output there. That's easy. So now we've got this big statement here. So P and R and Q. So although we could write this as P and Q go into an AND, and then the output of that goes into an AND with R, it's easier to just write a P, Q, and R all going into one AND, as this will only, as either way it'll produce the same output. So this produces the same output as two AND statements that would have two inputs each. So then that goes into an XOR gate, or an exclusive OR gate. And then it takes we've got Q XOR this statement. So we take an input of Q and the output of this AND gate, and it goes in here. Then the output of the AND and the XOR go into the OR gate, which produces our output. Now, just as some revision of truth tables, if you don't yet understand them, this is a very complicated example, but it's good to go over. So we've got the inputs here. This is every possible combination that you can have in a 3-bit binary. And this is important because this is how you want to see every output from a truth table. So again, you need to break this down. So first, let's do the P and Q. So that's in this column. So 0, 0, 0. But then down here, we've got two sets of 2 1s, which gives us 2 1s here. Then we've got P and Q and R. So that's this one here. And that produces these outputs. So only where all 3 of these are 1 do we get a 1, which is only the last row. Then we take the output of this and we put it into here with the exclusive OR. So only when we have one of either Q or this column as a 1 do we get an output. So we have a 1 here, a 1 here, a 1 here, and a 1 here. However, this row we don't get an output of 1 because we've got a double 1. And because it's an exclusive OR, that produces a 0. And then finally, we take these two outputs from the P and Q with an OR in the middle, and then we take this statement. So an OR gate produces a 1 if any or both of the inputs are 1. So here's a 1, here's a 1, here's a 1, and here's a 1. So there's the output. I hope that makes sense. Okay, now we come on to the Venn diagrams. Now a lot of these will be noticeable from maths, if you take maths. So A and B is the intersection here. But wait, sorry, let me first explain how these work. So the area outside is mimicking a 0, 0. Or A is, for instance, a 0, 1, and B is 1, 0, and in the middle is 1, 1. So that's where both are on. So an AND would produce an output if both are on, whereas an OR would produce an output if A or B are on, or both. Okay, so a NOT produces an output produces an output of inversion. So if you get A, it's everything that's not A. So now we come to NAND. So it's a NOT AND. Sorry. So the NOT AND produces this diagram here. We have a NOR, so it's a NOT OR, so it's the inversion of this diagram. Actually, my apologies, this diagram is wrong. This should have the outside filled in as well. So it should just be this bit that's white. I mean that this one's wrong as well. Anyways, so then we have this one here, which is the NOR gate. So it's the inversion of this. And then the exclusive OR should be this bit here white, and it should be A and B are white, not this one here. And then this bit should be filled in. Sorry for the confusion. Okay, so let's take an example here of P or not Q. And so first we have P. So we have P, which is, it will fill in this circle. And then we have not Q. So that's everything that is not inside Q, which would be this bit here. So it's all of this and then this section here. If you do maths and you understand Venn diagrams in maths, it's exactly the same. So we have P or not Q. So it's everything that is in those two. Okay, well, I hope you understand how these Venn diagrams and how to make a logic diagram. Thank you.